aviation fuel?
It is a key component to most modern-day aircraft, other than exceptions such as gliders, but we are not talking about that today. Aviation fuel enables aircraft to thrust through the air, even breaking the sound barrier. It is essential because, well,
It's not like airplanes can just fly magically. Like Harry Potter.
and just like gasoline for everyday cars, aviation fuels are made up of chemicals, the hydrocarbon compounds, and other additives.
But of course, there cannot just be only one single type of aviation fuel, right?
Obviously, a F-18 Hornet fighter jet is not going to use the same fuel as a small civil piston engine airplane. And there are also all these various kinds of aircraft as well. You got the military combat ones, the commercial airliners, the cargo aircraft. At the end of the day, those fuels got to have some differences somewhere in their chemical compositions, right? Right? How do the chemical compositions of aviation fuels influence the performance of an aircraft? Alright, first, what are aviation fuels and how do they work? Just like how you cannot drive your car when it is out of gasoline, the commercial plane you take cannot fly without aviation fuel. Whether it is a jet engine or a piston engine, they all require fuels to undergo combustion, which is a series of rapid oxidation reactions that release heat and usually light, occur in the gas phase, and result in carbon dioxide and water as the final products of complete combustion. There are multiple systems for fuels to be fed in the engine, and the fuels are mixed with oxygen, which comes from air, during flight in the desired ratio. Engines then convert the energy of moving fluids of hot, pressurized gas to mechanical energy, creating the thrust to propel aircraft forward. The main difference between piston and jet engines is that combustion is continuous in a jet engine and irregular in a piston engine, resulting in different combustion quality requirements and thus fuel requirements. Similarly to the gasoline used in cars, aviation fuels are petroleum-based fuels derived from crude oil, though they are designed to have a higher energy storage capacity, allowing long-distance flights. Conventionally, there are two main types of aviation fuels used in general aviation: jet fuels and avgas. Jet fuel is a refined kerosene-based liquid with a clear or straw-like color, primarily used to power turbine engines such as turboprop and jet engines. It includes Jet A, primarily in the United States, Jet A1, the most used jet fuel worldwide, and Jet B, primarily used in civil aviation. Avgas is used by traditional propeller aircraft and small piston engine aircraft, and usually for smaller scale tasks such as crop dusting, private flying, and flight training. The development of aviation fuel was much driven by the military's interest, and when avgas reached its development peak during World War II, it brought the rise of jet fuel, which is a much higher flash point, the lowest temperature at which the fuel can be vaporized and support combustion, than avgas, providing defense against fire hazards and accidents. Kerosene-type jet fuels were used at first simply because of their availability, and even though wide-cut jet fuels, Jet B, were also experimented with, the drawbacks of them made kerosene-type fuels, Jet A and Jet A1, the dominant fuel for most commercial aircraft. Though wide-cut jet fuel is helpful for flights at high altitudes due to its low freezing point, it also has higher volatility, including greater evaporative loss at high altitudes, a decreased chance of survival in aircraft crashes, and a higher risk of fire on the ground.
Long ago, the four nations lived together in harmony. Then, everything changed when the Fire Nation attacked.
Yet, Jet B is still used in some parts of Canada and Alaska, simply because of the cold climates, and is the most common alternative to Jet A, Jet A1, and avgas. On the military side, there are way more different fuels. Just for the US military, they have developed various avgas fuels in a whole series of jet fuels called JP, an abbreviation of jet propulsion. The two current fuels in widespread use by the US military are JP5 by the Navy and JP8 by the Air Force. After all, the primary goals for aviation fuel were always better reliability and more power. Now, time to break it all apart.
Oh wow, look at that. That is the perfect brake. I cannot believe that. It's a great brake.
Generally, aviation fuels are mixtures of many hydrocarbons, though there are many different molecular species and the current technology is not powerful enough to separate all individual species and analyze them. Though a good approximation would be 1,000 or more molecular species, with their range of sizes restricted by the distillation, freezing point, and other requirements. Out of all the different hydrocarbons, aviation fuels consist primarily of hydrocompounds such as paraffins, cycloparaffins, aromatics, and olefins. Paraffins and cycloparaffins are mostly the major components in bringing along the topic question of the influence of chemical composition. Their job is to reduce the freezing point of the fuel. While paraffins have a high hydrogen to carbon ratio with a high heat release per unit of weight and a cleaner burn, cycloparaffins have a low hydrogen to carbon ratio, resulting in less heat released per unit of weight, but increasing the fuel's density. Other than those two, olefins are similar to paraffins, but are unsaturated with lower hydrogen to carbon ratios. And aromatic hydrocarbons are good energy sources but produce smoke when burned. Due to that, the total aromatics content of fuel is controlled, especially the total naphthalene content, which is the simplest two-ring aromatic. These aromatics can form more carbonaceous particles that can be harmful to many parts of the engine if not completely consumed by the flame.
Everything changed when the Fire Nation.
Some non-hydrocarbon compounds, such as sulfur and sulfur compounds, may also be found in fuel. Though they are not needed for combustion and were not added to fuel in the first place, they were already present in the petroleum and were simply not removed during the refinement process. Even though they can form sulfuric acid and too much of that can damage the engine, they also allow the fuel to have better lubricity, which is needed in fuel pumps and flow control units, and they make up for the need for additional lubricity additives. In fact, additives are added to fuels in limited quantities to enhance and maintain important properties for fuel performance or fuel handling.
I am vengeance. I am the night. I am Batman!
These are the specialized fuel-soluble chemicals, including antioxidants, phenyl deactivators, fuel system icing inhibitors, corrosion inhibitors, and static dissipator additives. They typically originate from petroleum-based raw materials, and they are the principal difference between commercial and military jet fuels, with U.S. military jet fuels containing 3 or more additives, Jet A1 containing a static dissipator additive and maybe an antioxidant, and usually no additives in Jet A. The boiling point increase with the carbon number for compounds in the same class, and for the same carbon number, the order of increasing boiling point is isoparaffin, N-paraffin, naphthane, and aromatic, while the freezing point also increases with carbon number within each class. It is also strongly influenced by molecular shape as well. Avgas, still being gasoline in its root, has specific distillation and vapor pressure requirements that limit the boiling points, and therefore, the molecular weights or carbon numbers of the hydrocarbons, making the most common carbon number to be 8, commonly known as octane. Avgas requires the ability to resist knocking as it burns in the combustion chamber, which is basically abnormal combustion. The octane number scale can be used to measure it, and it is defined by 2 pure chemical reference fuels of normal heptane with an octane number of 0 and isooctane with an octane number of 100. The octane number is essentially the volume percentage of isooctane in the blend of these 2 compounds, although another scale called the performance number is also used. While isooctane is also defined as 100, above 100 is defined by mixtures of isooctane and tetraethyl lead, which is an effective anti-knock additive as it interrupts the chain reactions that lead to autoignition. Like mentioned before, Jet B is the choice in certain parts of Canada and Alaska due to the cold temperatures. This is one case where the choice of aviation fuel matters. Again, there are different types of fuels, so there needs to be some way to compare them. One of the measurable ways is through the energy content of fuel, which is the heat released when a quantity of fuel is burned. It is affected by fuel composition and can be measured gravimetrically in megajoules per kilogram or megajoules per liter volumetrically using the international metric units. For compounds of the same carbon number, the order of increasing energy content per unit weight is aromatic, naphthene, and paraffin by class, and the order is reversed in terms of per unit volume. Generally speaking, for military aircraft, a high volumetric energy content is preferred as it maximizes the energy stored in a fixed volume and provides the longest flight range. But for commercial aircraft, they do not require full tanks, and the choice between high gravimetric energy content and high volumetric energy can be complex and dependent. Other than the general uses we have stated previously, such as the use of Jet A in the United States, Jet A1 worldwide, and avgas for traditional propeller aircraft and small piston engine aircraft, the fuel choice made for commercial and civil aviation usually just falls under one or another. Though, the progression of technology keeps adding new aviation fuels to the list of choices and replacing older ones with stronger ones. In comparison with general aviation, the military puts in more resources into developing aviation fuels, experimenting with new ideas, and choosing the ones that would benefit the most.
Do you see a slot that would fit
The semicircle.
semicircle?
The semicircle.
That's right, it's the square hole.
And the desire for better aviation fuel has never stopped. Even today, people are still pushing forward for finer fuels, and this also includes new, emerging fuels that are more sustainable and eco-friendly, such as biofuels and hydrogen liquid-based fuels that are free of carbon emissions. Although overall, the choice of aviation fuel is really already standardized most of the time nowadays, which is a good thing after all, as the common aviation fuels being used today are already test-proofed throughout the decades, and systemized testing and regulations can be easily applied to ensure fuel quality and safety. Still, it is important for the pilots to understand the different fuels, especially the ones they are flying with. From what we have talked about so far, it is now quite easy for one to derive their answer to the original question. How do the chemical compositions of aviation fuels influence the performance of an aircraft? Without going through all the details again and re-mentioning absolutely everything, the two main types of aviation fuels today, jet fuel and avgas, are both hydrocarbon-based, though the differences in exact composition can impact the characteristics of the fuel, including examples from factors such as the use of different additives for specific purposes and the slight deviation in the percentage of paraffins in the fuel from the crude oil refinement, to the ratio of heptane, isooctane, and tetraethyl lead in avgas to obtain more output from engines, and kerosene-based jet fuels versus wide-cut jet fuels. Even though sometimes it is fairly clear how something can affect the fuel and one can more or less get the general image of fuel performance through some parts of the composition, like the total amount of naphthalenes or the percentage of kerosene to gasoline in a blend such as Jet B, other times it can be more troublesome, such as the sulfur and sulfur compounds in jet fuels, which indeed contribute to the lubricity of fuel, yet a low sulfur level in jet fuel is not a sign itself of inadequate and insufficient lubricity. In fact, the boundary lubricity of jet fuel cannot be simply predicted from bulk physical or chemical properties. One can only measure it in a specially designed test apparatus, and even fuels with similar sulfur and aromatic contents can have different lubricities. Aviation fuel is still a research field of study, and we humans do not know absolutely everything about making these fuels. Yet, through scientific observations, explanations, and reasoning, we can gradually learn and improve. At its root, it is a work of chemistry and combining different chemicals to achieve the best result. It is possible that one day we will reach the peak where the fuels cannot be physically improved anymore. But for now, the sky is where dreams happen. And maybe the next time you see a plane fly over and leave the smoke trails behind, you can better understand its power source, the aviation fuels. Thank you.